We heard yesterday Margaret MURNANE talk about these amazing developments in making, sources of coherent UV light and soft X-rays and actually very short pulses of these light sources. And today we are going to hear, I think, about some interesting applications. And the title of the talk is Capturing the Fastest Charge and Spin Dynamics in Nanosystems Using Tabletop High Harmonic Beams. Margaret, please.
Thank you very much, Lena. And thank you for coming back. And I'll try and, in the next two talks, talk about what can we do with this ability to generate coherent light at short wavelengths. And in particular, I also want to thank the students and postdocs who've really developed this capability. And now, after 10 years or so of trying to understand these spectroscopies, actually using them to learn things about materials that we couldn't discover in other ways. So it's an exciting time for me. They are making the discoveries, but we're finally, bringing this technology to where it can make an impact. And so, as Lena said, yesterday I told you how we make tabletop high harmonic beams, and today tell you one of the areas where the coherence matters. It turns out they're a really fabulous tool to use to try to understand correlated materials. And the reason is the energy scales are right. The exchange splitting, for example, in a ferromagnet is a third of an EV, or electronic excitation energies, phonon, timescales for phonons. All of those go from attosecond to femtosecond to picosecond. And we have that time resolution in these high harmonic sources. But the other thing that's very good is that if you really want to understand interactions in a material, you don't want to strongly perturb the material. And so a spectroscopy technique like photoemission, it turns out, is very beautiful, can look at the whole electronic band structure, and also use that technique to learn some new things. And then I'll just tell you very briefly about an unexpected finding about nanoscale transport and how you cool hot nanoscale objects. So just to remind you once again, why do people build synchrotrons, free electron lasers, X-ray facilities? Is because if you have soft X-rays, they can penetrate visibly opaque objects, and they have inherent contrast for elemental, chemical, and magnetic. And then when we have coherence, we can build diffraction limited microscopes, and there is no question that we now have the capability. We can make a measurement now with an attosecond precision, and only electron-electron interactions happen on that time scale. So today I'll talk about how we can understand magnetic systems and correlated electron materials using harmonic beams. And if I have time, I'll tell you about this crazy attosecond measurement technique where we've pushed down the measurement limit now to about a 10 attosecond lifetime. But I may run out of time, so maybe you can ask me the questions or something. But I try to focus this talk on, condensed matter questions. But I just wanted to give you the perspective that we're also looking at, measurements that are relevant to nanotechnologies. And for example, when we have a bulk hotspot, the way you would cool a material to cool a hot spot would be to surround it by a lot of cold material, and then you'd rely on diffusion to cool the hot spot. It turns out that your intuition is completely wrong when you go to nanoscale dimensions, because what our students found in the lab by just making the measurement, we weren't expecting it, that if you have nanoscale hotspots with dimensions smaller than the phonon mean free path in your surrounding cold material, that they cool faster if you pack them closer together. Got higher energy density per unit area, but what's happening, and we figured this out over time, is that they couple better to the phonon spectrum in the substrate. It looks like you have a uniform film, and so you can drive cooling very fast. So we could see this in the raw data. And so we had great fun being beaten up by the engineers who first said, you can't possibly be seeing what you're seeing. Then a year later, okay, we agree you see what you see, but we don't agree with your interpretation. And then 2 years later, okay, we see what you see, maybe you're right. So it's been interesting because, of course, our language for phonon transport and the way we calculate things, everything is different in physics and engineering. And so it was a great case of you really just had to go make the measurement and make the measurement, carefully, and not, what people had been doing is looking at nanosystems using visible light scattering and using a model to interpret the data. And of course, that's only as good as your model. And so it was a good example where, having a short wavelength light that could actually measure the actual temperature, or, that we were able to discover something new. So now I'll talk about some quantum material systems, and I need to apologize in advance to the condensed matter folks that, so this is something we've been learning, but we've uncovered some fundamental questions that we would love people's input on because we don't really know even how to ask the question properly. Okay, so what am I going to try and talk about? First of all, spin dynamics in materials. It's of interest because heat-assisted magnetic recording, there might be a direct way to manipulate a spin system with light. We know that from beautiful work by Theo Racing, that he can shine a single pulse of circularly polarized light on a magnetic material and switch the magnetization. But one thing we found is that the reason why there's been a lot of confusion in understanding the flow of energy in these systems is that it turns out that traditional spectroscopies are actually blind to some of the excited states, because a traditional spectroscopy is averaging over the whole band structure, but if you have a highly excited state, it's only in one part. And when they average, you just don't see what that excited state is. And this was something we fell over. We were not looking for it, but the spectroscopy and the ability of the students to notice something strange in the data and then go back and design a better experiment is how we were able to figure out that there was something very fast going on in magnetic materials. And then if I have time, I'll talk about how we can, again, use spectroscopies to understand how the charge and phonons interact in a charge density wave material. The surprise, there is that when you rearrange, when you drive a fast insulator to metal phase transition, that you couple only to certain phonons, and maybe that's not too surprising because in some of these materials there is a very strong electron-phonon coupling. The surprise was that the other phonons, it took more than 100 picoseconds to actually come to that same temperature. So the actual pathways were not what we anticipated. And then just as a comment, and again, this is a laser scientist commenting, when we got this ability to make attosecond pulses, many of us thought that the big applications would be in molecular dynamics. Turns out molecular dynamics are harder than dynamics in materials because the minute you put a charge somewhere it's not normally, you change all the potential energy surfaces. So the landscape has changed. You've got no constant. Whereas in a material system, the lattice, for the most part, in some cases, if you're looking at a sub-femtosecond dynamic, you preserve all the symmetry and nothing moves. Or if it's a charge density wave material and you're exciting a phonon, you have time to see the emergence of that phonon and you can actually watch the spectroscopy as it changes. So it turns out that it in some ways, attosecond spectroscopy is almost better suited for materials. We can also look at chemical dynamics using attosecond spectroscopy, but it's harder. it's harder theoretically to know what's happening. Okay, so let me talk a little bit about magnetism, and this is in very simple materials, just ferromagnetic materials, such as nickel. And of course, we all know that the magnetism spans many time scales all the way from geomagnetic reversal. But until about 22 years ago or so, people thought that the fastest motion in a magnetic system might be the precessional motion, which is on picosecond to nanosecond time scales. But just about when femtosecond lasers started to become in widespread use, Jenny Bigo was doing a sabbatical at LB&L, working with Chuck Shank's laser, and they shone a femtosecond laser on a ferromagnetic material and saw that the magnetism quenched in much less than a picosecond. And so immediately people started asking, how could this happen? Where did the angular momentum go? How is this happening? And was the material, changing from ordered to disordered? It was not at all surprising that you could excite the electron system on a very short time scale, but the spin system, people didn't really understand the mechanisms, and that is still true today. 22 years later, our collaborators often joke that every single year there's a paper that says we're finally solving this, the mechanism for ultra-fast laser-induced demagnetization. And of course, the reason it's challenging is that there are no first principles models. You have hot electron generation, electron thermalization, electron-electron spin flip, electron-magnon spin scattering. There's also superdiffusive spin transport. So there's a whole lot of mechanisms. You can arrange them in a sort of a order as a function of time, the very fast initial reactions, then the hot electron cooling, the spin flips due to collisions with phonons, and eventually the lattice heats. But it's a strongly coupled system with many interactions happening at the same time. So there is no first principle description. And it turns out that this was a beautiful paper by Bert Koopmans in 2010, and there's already at least 3 mechanisms that that the community can see in the data are happening, but aren't even on this little cartoon. So it's a complex system, and so without the ability to do a dynamic band structure, we try and devise experiments where we might be able to give some experimental input as to what is happening, and then go to our theorist colleagues and sort of say, well, does this help in elucidating mechanism? So the experimentalists would try to, take this very complex system and do a very sort of crude phenomenological 3-temperature model, where, of course, the electrons their heat capacity in the electron bath is much smaller than the lattice. So the electron temperature spikes up to thousands of Kelvin, and then they would start to interact with the spins and phonons. And electron-phonon interaction is somewhat well understood, but how to describe the spin system was not at all well understood. So for a long time, people thought that there was some mechanism, whether it be via phonon coupling or such, where the spin system would heat, or the temperature would increase well after the electron temperature spiked, which is a little bit non-intuitive, but that's what the spectroscopy was telling people. I'll show that in a moment. And the type of mechanisms people were trying to distinguish between were this, you would heat the electrons, and then, because in a ferromagnetic material, the spin up and spin down mean free paths were different. You could have a super diffusive spin current that would demagnetize the material, and that was one way of losing magnetic order. Another were spin wave generation, such as magnons, and another one would be the reduction in the exchange splitting. And so this would be a local mechanism, and this would be, magnons would be a non-local distributed magnetic moment. Okay, so so before I tell you how we tripped over some observations that helped shed some understanding on this topic, let me first show you how we make the measurement. So we have our high harmonic comb, and even in the extreme ultraviolet region of the spectrum, there's many magnetic absorption edges of these ferromagnetic materials here at the M edge. So we can sensitively probe the moment on nickel, cobalt, iron in alloys or in multilayers, and even in the EUV, the light can penetrate tens of nanometers in these materials that are opaque to visible light. And if you do a visible magneto-optic spectroscopy, you probe the average moment, whereas in the EUV, you can probe the local moment on each element in an alloy or each layer in a multilayer. So you can then distinguish between different mechanisms. And the signal is huge. So what we do is we have our magnetic material, we use an ultrafast laser to heat the electron bath and then probe using the whole high harmonic comb, and then either on the sample or after the sample we'll put a grating and then read out the reflectivity, and the reflectivity through the magneto-optic effect depends on the magnetic state of the material. And this is on a linear scale. This is the type of signal. So the dashed and dotted lines are just a static reflection from a magnetic material as we use a pair of Helmholtz coils to change the direction of the magnetization. And then we calculate the magnetic asymmetry, which is the change in the magnetic moment normalized, so we have a background-free signal. And then that's what's plotted here in purple and yellow, showing this was multi-layers of iron-nickel, showing the static magnetic asymmetry. After we heat with a femtosecond laser, we're destroying the magnetism, and if we completely quench the magnetism, then you would just get a straight line. So we can monitor the magnitude of that signal, and it's an extremely strong signal. Okay, so one of the first experiments we did was to try to distinguish between two very different mechanisms for how the magnetization was being quenched. And one of them was a spin flip scattering, just some interaction between the charge and phonons that allowed the spin to flip and take away the angular momentum. And another one was this superdiffusive spin transport, where you can think about the ferromagnetic material spin up and spin down, but because the mean free path or the collision time is longer for the two different spin baths, the spin up electrons can travel further before a collision compared with the spin down. This would take away magnetic moment, not destroy it, but just take it away from your probed region. We figured these mechanisms are very different. We surely can do an experiment that would allow us to distinguish between these two, because one is local, one is non-local. So, and condensed matter folks can forgive the simple cartoon, but it's in one case we heat the material and you randomize the spin. In another case, you heat the material, you get a spin polarized current, but your return cold current for charge neutrality is not spin polarized. And so that way it looks like you demagnetize the material, but you didn't. So with our colleagues at NIST, we set up a little experiment where we had a nickel layer, a conducting layer, but non-magnetic, and an iron layer. And the femtosecond laser can penetrate all of these layers, so we heat up the electron bath in all of these layers and then see what happens. And if the mechanism was completely local, you would expect to quench the magnetization in both layers. That's not what we saw. So what we saw in the experiment is we had fully magnetized the two layers initially, and what we saw was that the nickel layer, the magnetization quenched, and in the iron layer, the magnetization increased, or seemingly increased above the maximum value. And you think about this and you say, well, there is no way you can do this if you don't have spins flowing from the nickel to iron. And in fact, we then reversed the direction, and in that case, actually in this one, we had an anti-ferromagnetic coupling where the spins in iron were in the opposite direction from nickel, and in that case, both the magnetization quenched in both layers. So our colleagues in Jülich and Uppsala said immediately, oh, so this solves the question. It's all the demagnetization must be due to spin currents. But fortunately, we had a good student who thought, well, maybe we should do one more just careful experiment to see if we can see multiple mechanisms working at once. And so we did this series of experiments where we had the same multi-layers, but now spaced by conductors, spin scatterers, and an insulator where there would be no spin currents. And what you found is when you stopped the spin currents, you quenched the magnetization in both iron, the buried iron layer, and the nickel layer. And there is no way this can happen unless you have two mechanisms at work. That because there was no spin currents going from nickel to iron, there must be a local spin scattering mechanism within the iron layer. And
how are you measuring the magnetization?
Just with this measuring the change in reflectivity. It literally is this just what we showed here. So what you measure the asymmetry, which is the difference in the reflectivity for in two different directions of the Helmholtz coil. So we could have magnetization in plane in two different directions. And then after you heat the material with the femtosecond laser, if there is quenching of the magnetization, the difference between these two curves goes to 0. And so this is a magnetic asymmetry plot. It is flat everywhere except at the iron M and nickel M edges. So it lets us monitor very sensitively at the same time what the magnetic moment is in each of those layers. Thanks, Isaac, for the question. So that's why we can be, very, we can measure very sensitively that when we allow spin transport, the magnetization in iron increases. When we prevent spin transport, the magnetization in iron decreases. The only way you can explain that is that there are spin currents happening and spin scattering at the same time. And when you actually analyze the magnitude of these contributions, which you can do from this data, they're actually equally important, which was very nice for us as new people, relatively new in the field, because it turned out that both theorists were right, but they had been proposing independent, separate mechanisms, and the data showed that there were multiple mechanisms happening at the same time. But this data bothered us a lot, Tom Silva at NIST, because if, on the one hand, it's fairly clear there has to be two different mechanisms. But from a physics point of view, if this was due to a spin transport, if this increase in magnetization was due to spins rushing from nickel to iron, and if this demagnetization was due to spin flip scattering, which can take a while because you have to conserve angular momentum, it seemed very odd that all the timescales were exactly the same. And they're very different microscopically. And it bothered us, and but everybody else was in the same boat. No, nobody could really explain it. And then, so we fell over the answer to the question. So, so this is what everybody does. You have a very short laser pulse, and then you see quenching much later. And so there's always this fall time and slow recovery dynamics. But, we weren't actually getting at, well, what's the ultimate speed limit? Was this even ferromagnetic to paramagnetic phase transition? It wasn't clear what you were doing to the material, what determines the time scale, why does it take so long? Because, 500 femtoseconds is sort of an odd time scale in material. If it's charge and spin coupled, which you would expect in a ferromagnet, it should be much faster. If it's coupled to phonons, it would be much slower, because those are just the coupling times from the different baths. And so this was sort of an intermediate time scale, so it was very odd. And so what I'll tell you over the next few slides, I'm going to try and convince you that is what's happening with this laser-induced phase transition is almost exactly the same as what happens when you heat a ferromagnet above the Curie temperature. And let me see if I can persuade you of that. And so what we did with photo emission is to measure the electron temperature as a function of laser fluence, and you saw this very suspicious kink when the electron temperature reached the Curie temperature. And so let me try and see if I can make the case for what we believe is going on. So to prove, and this happens 24 femtoseconds after you excite the material with a laser, which means that energy is going into the spin system almost instantaneously, but it doesn't. You can't see that excitation in a traditional magneto-optic spectroscopy. So this is how it was Kong Chen and Phoebe Tengden, two grad students. One of them was working on a photo emission experiment, the other one working on the magneto-optic experiment. They decided to get together and use the two different probes on the same material and compare. And so this is the magnetic asymmetry I was talking about earlier that we can get with the magneto-optic spectroscopy, which measures the dynamic, the instantaneous bulk magnetism in the material. But we also had a photo emission apparatus in our group, and initially we were not so good at it, so we had a lot of space charge broadening, but even with that poor energy resolution, we could still see the spin split bands. This is a typical angle resolved photo emission spectrum near the Fermi level, and these are the two, the D band and this is the exchange splitting. So we can monitor the exchange splitting as a function of time. And the thing to note is that this angle resolved photo emission, it measures the surface band structure exchange splitting, and we can take a line out so we can fit exactly to what the electron temperature is. We don't need a model, we just fit the Fermi-Dirac distribution. And you get, the nice thing is that we get exactly the same behavior from the two different spectroscopy techniques. So that was the first good news. We thought, if you measure the time scale for collapse of the magnetization, we would get about 150 femtoseconds using both techniques, and they both gave us the same number within error bars. So that was our sort of sanity check. Could we reliably measure the characteristic of the material with the two different probes? But this was the measurement that really gave a clue as to the mechanism. So what this is the from our photo emission data, we could measure the exact electron temperature by fitting the Fermi edge, and then plot that as a function of laser fluence. And we're plotting this peak temperature. This is the Curie temperature here for nickel. We're plotting this 24 femtoseconds after we irradiate the material with the laser. and you get this kink. Now, if there was no contribution, of the heat capacity of the spin system, you would expect the electron temperature to follow this purple curve. But because the electron temperature is not increasing as fast as you would expect, the difference here is the heat capacity in the spin system. So although with the magneto-optic spectroscopy, it's taking around 200 femtosecond for the magnetization to collapse, the energy is going into the spin system within 24 femtoseconds, much faster than you get the spectroscopic signature. We could extract, from this data, we could extract the heat capacity, and sure enough, you get this critical behavior that as you might expect. This was the exchange collapse, and that happened only above this critical fluence, at which point you had heated the electrons, just the electrons, not the lattice, but you'd heated the electrons above the Curie temperature. So the conclusion is that the light excitation gets coupled into the spins within 20 femtoseconds. We need to do the experiment with higher time resolution to know how quickly if it's directly associated with the excitation or if there is a response time. But it takes 176 femtoseconds for the spectroscopy signals to show you that the magnetization in the material has collapsed. We did another sanity check. We cooled the material to 100 Kelvin, and sure enough, you get exactly the same behavior, but it just takes, but at a higher laser fluence, and it's still the laser fluence at which the electron temperature is heated above the Curie temperature. So so now this is the hand waving part, because we don't actually understand, and we've asked our theory collaborators, but we don't understand what is the nature of that highly excited spin state. So this is the cartoon we came up with just to put something on the table. So if you heat the material gently to where you don't drive the electron bath above the Curie temperature, you'll get a few, let's say, we call these high energy magnons, because remember, if you heat a magnetic material slowly, then the lattice, the spins, and the charges are all at the same temperature, and you're going to generate some disorder in the spin system, but it's not going to be a highly excited disorder. But when we come in with photons, then if we are able to, through some mechanism, whether it's a superdiffusive spin transport or some such mechanism, flip spins, that's not a normal state that you would find the material that you can get to in equilibrium. So then, but if we're below some critical density for spin excitation, then the material recovers very rapidly. If it's a phase separation, you could think about just having a small few regions demagnetized, and then the rest, the recovery is fast. But above this critical laser fluence that drives the electrons above the electron temperature, above the Curie temperature, then we're postulating that there's we're above a critical high energy magnon excitation. That takes 200 femtoseconds to for energy to flow to a more distributed set of low energy magnons, and that's when your magneto-optic spectroscopy will tell you the magnetization has collapsed. But in fact, all of the energy transfer happened on a much faster time scale. And so what this showed us is that traditional spectroscopies are not great at finding these superexcited states, because they're averaging over the band structure, and your excitation might be in a different form. Okay, so in the second material I'd like to talk about, and this is very new work, so we don't have our explanation so smooth, so you'll have to forgive me, but I wanted to give it as another example of where the material was doing something that we didn't understand at all. We didn't even know we should be probing it, and it was just a smart, some of the smart grad students who saw the signatures in the data that then allowed us to apply a better version of the spectroscopy to know what was going on. So if I we with our collaborators, Martin Eschelmann's group in Kaiserslautern and Michael Bauer's group in Kiel, we started looking at charge density wave materials. These are very interesting to look at with very short pulses because the interactions are strong. They're driven by charges and phonons, so they're great for a technique that can probe 100 femtoseconds and faster. And if we look at this general class of materials, excitonic or Peierls charge density wave materials, depending on the nature of the electron-electron interaction, whether the electron-electron interactions are stronger or the electron-phonon interactions are stronger. One thing that you might speculate in these materials that you might be able to look at what are the dominant interactions by just looking at their response time. If it's an excitonic material, you should be able to see a response on order of 10 to 100 femtoseconds, whereas if it's a Peierls-like insulator, because their electron-phonon coupling is dominating, it should take hundreds of femtoseconds for the material to respond. So these materials are of interest for fast switching materials. And what we're discovering is that these high harmonic angle resolved photo emission techniques are very sensitive to these couplings. So there's some beautiful work from Ziek Shen's group in Stanford, Martin Eschelmann's group in Kaiserslautern in angle resolved photo emission. And the wonderful thing about it is it really lets you map the unoccupied bands, both the occupied and it can also tell you about the unoccupied bands in the material. And there's this little a sentence here most of the time, because there's one time where it doesn't work well, but that's also interesting. But I may or may not have time to talk about that. So in the initial experiments, these are typical angle resolved photo emission spectra. And the condensed matter experimentalists get very good at reading these. Instead of showing you the whole spectrum, I'll just show you a line out that just gives the response time of the material. So heat the material with a femtosecond laser and see how fast you can take that material from insulating to metallic. And then by looking at that response time, if it is very fast, like 20 femtoseconds, and doesn't change with how much carriers you're putting into the unoccupied bands, then you can sort of say it's a Mott-like insulator. If the response time decreases as you increase the laser fluence, then you can say maybe it's excitonic-like. And then if it's relatively long, longer than 100 femtoseconds, and doesn't change with how hard you hit the material, you can sort of say that maybe this is a Peierls-like interaction. Now, this is a very simplistic way of looking at it, just seeing if you can classify the material according to the time scale of the dominant interactions. But since then, we've gotten a little better, because what we can do is look at the data across the full band structure, because with high harmonics, the photon energies are high enough that we can actually map the whole Brillouin zone. And then look at how the different order parameters change. And so in new work, what we did is look at this tantalum diselenide material, where the electrons in the insulating state, and after you excite with a femtosecond laser, the charge gets redistributed spatially. And so think about that. That's a very big change in charge distribution, and you're going to excite phonons when you do this. And in the past, people would have thought that there would have, just oversimplifying it, that you might excite many phonon modes when you did that. what we find is that actually after excitation, you only excite a small number of phonon modes. So essentially this is from some other work showing how the charge is redistributed after you laser excite the material. And so what we can do is, again, look at, as the material goes from an insulating to metallic, we can look at the gap, melting of the gap. And we can also look at the electron temperature like we did with the ferromagnetic materials. And we can actually plot, for example, the band shift as a function of fluence. And we can actually associate this oscillation with a specific phonon mode and see that actually what we're doing after you smear out the charges, you launch a certain phonon mode and you actually modulate the electron-phonon coupling. That's changing. This is perhaps not too surprising in a Pyres-like material, because this is this is the whole nature of that material. But it was interesting. So this is what probably the newest thing is that this hot phonon excitation lasts for about 100 picoseconds. So you take your material in an insulating state, excite the electrons that then, because it's charged density wave material, will be completely spread out. That's a very strong kick to the phonons. You excite this transient charge density wave material state that lasts for about 100 picoseconds, and then only after a nanosecond do you get to the place you might have gotten to if you had just heated the material and kept both the charges and phonons all at a single temperature. You can see this is a highly non-equilibrium state with a mode-selective electron-phonon coupling. This is a new transient charge density wave state that you couldn't reach from equilibrium. And we are playing around trying to see how best to represent this as we're preparing this material for publication. And you can see this is going to be hard because it is a complex story. Not surprising, because these are complex materials and hard to understand. Okay, so if I can talk for another 5 minutes, I'll end with the crazy attosecond experiment that perhaps doesn't connect as well to condensed matter, but is a measurement that I would not have expected that we would be able to make. And it's this, so how do you use the fact that we've got these incredibly short pulses? But if you used a single pulse, you would lose all state selectivity, because the bandwidth for example, a 1 attosecond pulse would be KeV. And there you would just average over everything and not be able to compare with theory. Okay, so I showed this slide yesterday of, well, what could we look at? Are there things that happen? And what I'm going to talk about is hopefully electron screening and scattering, and how would we make that measurement. And we have to make the measurement in a band-specific way. That's how the electrons see each other, so it has to be in a band-specific way. But if you look at this band structure in nickel, and these are in electron volts, 100 millielectron volts it's not great for a superconducting material or a topological insulator, because there you'd like 1 to 10 millielectron volt precision. But if you want to do time resolution, you have to preserve the uncertainty principle. So we would be happy if we can keep 100 millielectron volts, and that gives us energy resolution, and that would correspond to a few femtosecond time resolution. But the question is, how do you make the measurement, and under what circumstances should you use an isolated burst or a sequence of pulses? And so what our claim now is, if you want to make a few femtosecond measurement, then you would like to arrange it that your laser pulse makes a single attosecond burst. But if you want to make a true sub-femtosecond measurement, and And if it's electron dynamics, so the dynamics are over in between your attosecond bursts, then what you really want to use is a sequence of attosecond pulses. In the spectral domain, then you can have high energy resolution, but because you've got isolated bursts, and these are not Gaussian pulses, you can still get very high time resolution. So let me explain how we do that. But first of all, what can we look at? So there are excited states in the band structure of materials that are not normally occupied. Photoemission folks know about these excited states because they stay away from them like the plague, because in photoemission, we're trying to look at the energy distribution of electrons that come from, you would think, the normally occupied states. But if you look at this photoemission spectrum that was taken by Wolfgang Eberhardt, as he tuned the photon energy in a synchrotron from 100 eV to 150 eV, normally with photoemission, you should just get an exact copy that just plot out the occupied state of the materials. But in some regions, you get these resonances, and they are super broad. And they have 4 eV line widths, and that is a very fast lifetime. And in fact, they're universal, and they're in many materials. This is in copper. The line widths go up to 15 eV or so, and that corresponds to a state with a 200 attosecond lifetime. And so how do you measure it? So we use our angle resolved photoemission, but we have to play a different trick than the data I just showed, where what we have to do is, and I apologize for the acronyms, we have a big contingent in France who love animal acronyms. So we have to combine laser-assisted photoemission with angle and resolved photoelectron spectroscopy and RABBIT, which is a quantum interference technique. So let me show you a schematic of how we do that. Okay, so what are we? Oh, there's a missing. Interesting. There's a missing. What happened there? That's good. That is interesting. Okay. So there's definitely unoccupied bands there because there's no bands, and I can't show you the. Okay. Let me show you here. At least you can see the experiment. Okay, so this is the experiment. So we have occupied bands, unoccupied bands. Some of the these are and you can photoemit into an unoccupied band or into a free electron final state. And what we can do is measure the time difference between photoemission through these unoccupied excited states with very short lifetime compared to a free electron final state. And how we do that is it's this quantum interference that we, of course, if you just do photoemission, you don't know when the photoelectron came out. You can record its energy, but you don't know when it came out. But what we can do is shine a femtosecond laser on the material, on the surface of the material, at the same time we shine our high harmonics. And the photoelectron can absorb, for example, this photoelectron can absorb an infrared photon. This photoelectron can emit an infrared photon, so you get multiple quantum interfering pathways that link the two states. And we can measure a phase shift, and that phase shift then can be translated into a time delay. And that lets us measure the lifetime of the state. So it was a great, because we knew the line width, so it was a great thing to learn how to do the measurement on, and that's what's plotted here. You can see just where we expect the resonance, we see this 200 attosecond time delay. And so it's very clear. And once we learned how to do that measurement, then this is something for the ultrafast folks. People got upset with us because they thought, how are we having high energy resolution and high time resolution at the same time. And the reason is that our light is sort of, it's a sequence of attosecond pulses. So we don't know from which pulse the photoelectron comes, but it doesn't matter because we're just measuring quantum interfering pathways. So then we are actually giving up information on from where in the pulse the photoelectron came. And so that's how we're not actually violating anybody's principles. It's a legitimate measurement, and we can measure the band dispersion, which is an interesting technique because it's hard to measure the excited state band dispersion using other approaches. And then finally, in the last few view graphs, let me tell you, so we then try to apply it to measure something that's hard to measure, which is distinguishing between electron-electron screening and scattering. So we did the same measurement in copper and nickel, and we saw a difference in the excited state lifetime. That's not at all surprising. There are different materials, different band structures, different line widths. But we noticed there was also a difference in photoemission of 100 attoseconds off resonance. And there must be some mechanism giving rise to that. It's not the excited state. These are interfree electron final states. So the question is, why did the electrons take longer to be photoemitted from copper than nickel? And if you're trying to explain a 100 attosecond time scale, you can only invoke electron dynamics. Nothing else is doing anything on that time scale. So it had to be either more screening for electrons trying to leave copper, photoelectrons trying to leave copper, or enhanced scattering for photoelectrons trying to leave the nickel. And scattering, of course, will decrease the lifetime. Screening would increase the lifetime. And so we compared with theory, free electron gas, looked at the band structures. You realize copper has a full D band, nickel has an exchange split band, and there are more final states available for scattering into. So then that it made very good sense that as the photoelectron tried to leave the nickel, then the Baer-Coulomb interaction matrix with other electrons could cause this electron to lose energy and excite another electron. So it showed that very likely increased scattering in nickel were the reason. But then we tried to use that information and connect it to something people might be interested in understanding, which is that Baer-Coulomb interaction matrix that we can measure using this technique is not so energy dependent. So we should be able to extrapolate our data down to the Fermi level. And so this is our attosecond RPs measurement, measuring lifetimes on order of 10 attoseconds. This is 2-photon photoemission measurements. In copper, the same Baer-Coulomb interaction matrix explains all the data, all the way from the Fermi level to high photoelectron energies. In nickel, you need two different Coulomb interaction matrices to explain the data, and the difference has to be due to strong screening, which is known to be at work in nickel because of its complex Fermi surface. But this gives a way of actually quantifying the contributions of screening near the Fermi level. Okay, so I hope I've shown you that we are able to make some measurements at really extremely high time resolution, and we're learning how to use those measurements to learn something about interactions in correlated materials. Tomorrow I'll talk about using the spatial resolution of high harmonics to push imaging to its limit. I hope I've given, made a case that we have a tabletop technology that's complementary to synchrotron sources. This is the size of the system that can be used for photoemission. So it's actually quite small. And of course, of course, one of the big applications are trying to learn how to manipulate materials and change their phase on demand. That's a goal of a lot of research in DOE. And with that, I need to thank the students, postdocs, and collaborators who worked with us on this quantum material efforts. In particular, Kang Phoebe, who this was their thesis work, and two amazing postdocs, Zhensheng Tao, who's now at Fudan University, and Junxi, who's in Boulder, Tom Sova, our collaborators from NIST, Peter Oppenir, our collaborator from Uppsala, Martin Eschenman, collaborator from Kaiserslautern, and Manos Mavroukakis, who did band structure calculations for us. Thank you very much for your attention.
Thank you, Margaret. So we do have time for questions here.
Margaret, when you say that you can see things when probe magnetism that we can't see with an optical probe, you mean specifically photoemission spectroscopy. That is, if you simply are probing an absorption edge, then do you see exactly the same as with MOOC?
So if you use visible light to do a magnetooptic spectroscopy, it averages over the magnetic moments of all the different elements. So in an alloy, you average. Or in the multilayer, you would average.
So multilayer can probe from opposite sides, let's say.
Yes, you can probe the surface using visible light, yes. But in an alloy, you don't see it. And in this multilayer, in many experiments, you know, if you can measure at the same time, you can see very small differences, so it lets you see the energy flow. If you have to do two separate measurements, then, for example, in a synchrotron or X-FEL, you would not have, the jitter is too large. You couldn't translate the data from one measurement to another.
Oh, so you're using the two wavelengths in a single measurement?
Yes, we shine the whole comb, so we take all the data at the same time. So when you see a time shift, you know it's not an artifact in the data. And, you know, it does make sense there would be very fast dynamics in magnetic materials. That's not so shocking. I guess what was a bit shocking is that for 20 years, we were measuring the wrong thing, you know, because, you know, the chemists, Casey Hines always says at Boulder, every measurement should tell you something different because you're measuring a different thing. And this was particularly true here in these material systems.
Yes, I didn't quite follow what the reason for using a 3 attosecond. If the 3 attoseconds corresponds to a bandwidth of kilovolts,
KV, yeah.
Why do you want to use 3 attoseconds rather than 30 attoseconds or 50 attoseconds or 100 attoseconds?
Okay, so you're right. It wouldn't matter. It's for those of you, if you know the chirp. So if you want to do, for example, a time-resolved XFs or NEXFs, then in principle you should be able to see, you know, charge transport because there's going to be a chemical shift at the edge. So you could see it, say, in a superconductor or some oxide material, and you can clock that, you know, change in the material if you know the supercontinuum, the chirp on your X-ray supercontinuum. So you don't need to compress the pulse. This is a standard trick used in many ultrafast spectroscopy techniques. Depending on the spectroscopy you're doing, if it's photoemission, if it's a magneto-optic spectroscopy, if it's an XF spectroscopy, then you want a supercontinuum. And there you would like the 1 attosecond, or you would like you wouldn't care if it's a femtosecond probably, or if it's chirped to a femtosecond, or if it's 3 attosecond or 30 attoseconds, you don't care. The physics of the process means it does tend to emerge chirped.
I'm sorry, I still didn't understand. Are you taking advantage of the fact that your excitations, I thought, were all in the range of tens of electron volts. You're not using, let's say, X-ray excitations.
No, everything I talked about today was...
Why do you need to... So what, I still haven't understood that. I'm sorry. What is the advantage of using 3 attosecond. The 3 attoseconds means that you have frequencies all the way up to very high frequencies, but you're not using those frequencies, if I understood correctly.
Correct. I didn't show work today that used those frequencies. We have work that looks at XFs that uses KV light, that we use light throughout the whole soft X-ray region to take the near edge absorption fine structure and extended edge absorption fine structure. I just didn't talk about that today, but you're absolutely right. In most measurements, a femtosecond time resolution is fine. So you don't need to compress the pulse, and moreover, there is no way to do it. Because
but also you're not using the high frequencies.
we did use the high frequencies in XFs. I just didn't talk about them.
Okay.
Yeah.
Okay, any further? No? Let's thank Margaret again.
Thank you, Lena.